Today we're going to look at two types of chemical groups, which are very important in chemistry and everyday life. Acids and bases. We'll look at properties and uses of acids and bases, what are acids and bases, the pH scale, indicators, acids and bases, conjugate pairs and strengths, and common reactions of acids. It's surprising how many acids and bases are all around us. This is my house. I've got a few chores to do today. Like cleaning the oven. My goodness, how does it get so filthy? It's all the splashes of hot oil, fat and sugar residues, to name a few, that get baked onto the inside of the oven. Ta-da! Oven cleaner is a base, or alkali. It's corrosive, and that's why it's useful for cleaning away all this muck. Next, I've got to put this old car battery out for the special trash collection, because you see, that's my new battery. You can't put this out with regular trash because it contains sulfuric acid, which can burn skin, eyes, and other things because it's corrosive. So acids and bases can be both corrosive. That's a property they share. That's why I wear gloves and goggles when I use oven cleaner. Ever heard of acid rain? In certain parts of the world where the atmosphere is polluted, falling rain dissolves different substances as it moves through the atmosphere and onto the earth. Chemical compounds like sulfur dioxide and nitrogen oxides, which are typically given off by the burning of fossil fuels. When the rain hits the earth, it is naturally acidic due to the presence of dissolved carbon dioxide. But if it falls through polluted air, it becomes even more acidic, because sulfur dioxide reacts chemically with oxygen and water to form sulfuric acid, and nitrogen dioxide reacts in a similar way to form nitrous and nitric acid. It causes corrosive damage to things including trees, buildings, and statues. Acids and bases share the property of being corrosive, and yet they react together as opposites and neutralize each other. Remember the antacid I was eating before? It's an alkali. When you get heartburn, it's acid from your stomach coming up your esophagus. The antacid neutralizes the acid and takes away the burning. Vinegar is a weak acid. It can be used for cleaning. It's especially good on smooth, shiny surfaces like tiles and glass. Acids also kill bacteria. On these tiles around the bath, sometimes there's a buildup of soapy residue. Funny to think that soap needs cleaning away, isn't it? Anyway, vinegar is ideal for removing it, because soapy residues are alkaline or basic, and vinegar, being an acid, neutralizes them by breaking down the soap scum to make it more soluble. Sometimes acids and bases behave in a way that's colorful. They cause a color change in an indicator. Watch. First the acid, in this case it's nitric acid, or HNO3. Then the base, which is sodium hydroxide, or caustic soda. That's NaOH. Color changes in indicators are used in analytical chemistry where acids and bases are involved. Some acids and bases are good conductors of electricity. This is because they form electrolytes in solution. there is enough concentration of ions in solution to conduct current. Remember the car battery? The sulfuric acid is the electrolyte. And that just gets us started. Acids and bases share some properties. They can be corrosive. They react together and neutralize each other. Sometimes salt and water is produced when they react. Both are used for cleaning. They cause color changes in indicators, which is useful in analytical chemistry. Certain types form electrolytes in solution, so they conduct electricity. Hey, a postcard from my friend in Sweden. Cool. Sweden was where a 19th century scientist called Svante Arrhenius lived. He came up with an explanation for why acids and bases have their properties. Arrhenius observed that acids and bases neutralize each other in aqueous solutions. He said it was because they both release particles into the water, acids releasing hydrogen ions, and bases releasing hydroxide ions, which join together to make water, or H2O. Now Arrhenius was on the right track, but his theory didn't explain why the ions were released by acids and bases, and it didn't explain why neutralization still occurs even if there is no water present. Now, if we could look up close at acid molecules, I mean really close, we'd see that they have some things in common, like hydrochloric acid, or HCl, and nitric acid, or HNO3, and sulfuric acid, or H2SO4, and acetic acid, or CH3COOH, which is also known as vinegar. At least one hydrogen atom in each case is joined to a highly electronegative atom, like oxygen or chlorine. These bonds are covalent bonds, bonds made by the sharing of electrons. But the one electron that hydrogen contributes to the bond is only weakly held by the hydrogen atom because of the strong electronegativity of the chlorine or oxygen atoms. Now, if hydrogen loses an electron, what we have left is a proton. There's only one of each in a hydrogen atom, remember. And this is what happens to the H-positive ions, or protons, when they combine with water. We get H3O forming, or hydronium ions. So Arrhenius's explanation doesn't quite fit here. Enter Johannes Bronsted and Thomas Lowry. Bronsted lived in Denmark, and Lowry lived in England. In 1923, almost at the same time, and quite separately from each other, Lowry and Bronsted proposed the theory that we still use today to explain acids and bases. Can you guess what the theory is called? The Lowry-Bronsted theory. It says that an acid is a substance that donates protons, and a base is a substance that accepts protons from acids. But an acid can't behave like an acid unless there is a base there to take its protons. Let's look at an example. Here, we're adding aqueous sulfuric acid to aqueous sodium hydroxide. Sulfuric acid ionizes in water to produce hydronium ions. Sodium hydroxide dissociates in water to produce hydroxide ions. Hydronium and hydroxide ions then complete the acid-base reaction. For simplicity, it's easier to write the overall equation. And a final point, some acids are polyprotic, meaning they can have more than one proton they can donate. Look at the formula for hydrochloric acid. Each molecule has only one proton it can give. It's monoprotic. But sulfuric acid, H2SO4, is diprotic. And phosphoric acid, H3PO4, is triprotic. The in-between products of polyprotic acids are called amphiprotic substances because they can go either way. They can donate another proton, or they can accept a proton to replace a donated one. So they can act as acids or bases. Water is also an amphiprotic substance, as it can react with acids or bases. Arrhenius's theory said acids and bases release ions which bond and form water. It didn't fully explain acid and base behavior. In acids, hydrogen atoms share one electron with strongly electronegative atoms. They can be drawn away, leaving the electron. A hydrogen atom, minus its electron, is a proton. Lowry and Bronsted theory says acids donate protons and bases accept protons. Polyprotic acids have more than one H+ to donate. Amphiprotic compounds can donate or accept protons. If you've got a swimming pool at home, you've probably tested the pH of the water. pH is a measure of the concentration of hydronium ions, or H3O ions, in a substance. Sounds complicated, doesn't it? The concentration of hydronium ions in different acids and bases involve pretty small numbers. We talk about them in terms of logarithms, or powers to the base 10. And typically we get values like 10 to the negative 3, 10 to the negative 5.4, 10 to the negative 7, and 10 to the negative 13, just to pick a few off the top of my head. But we talk about pH values as being positive numbers, not negative. So the actual index number in each case is the value of the pH, without the negative sign. For example, if we find that the concentration of hydronium ions in a solution is 10 to the negative 3, the logarithm in this case is negative 3, so the pH is 3. A low pH means a high concentration of hydronium ions, and a high pH means a low concentration of hydronium ions. Finding that hard to grasp? It helps if you look at a pH scale, like this one. It goes from 0 to 14. That means the concentration of H+ ions varies from 10 to the 0 to 10 to the negative 14. The lower numbers are all associated with substances that are stronger acids. The higher numbers are all associated with substances that are stronger bases. And 7, right in the middle, is neutral, neither an acid or a base. You know it's got a pH of 7, don't you? Water, of course. pH can be measured in different ways in the lab, like with universal indicator, where you match a color to the pH reading, just like the one you might have used on the swimming pool at home. It can also be measured with a pH meter, which gives a readout of what the pH of a substance is. 7. just as I suspected. Here are some examples of substances and their pH values. pH refers to the negative logarithm of the concentration of H3O ions in a substance. A low pH means a high concentration of H3O plus ions. A high pH means a low concentration of H3O plus ions. The pH scale goes from 0 to 14. Strong acids have a low pH, and strong bases have a high pH. Water is neutral, with a pH of 7. Want to see me turn this water into wine? Cool, huh? Actually, what I really did was added some strong base to a little bit of weak acid, which you might have not noticed in the glass. The weak acid is called an indicator. In this case, it was phenolphthalein indicator. Try saying that 5 times quickly. Indicators are a way we can detect the presence of acids or bases. They are usually weak acids, which take on one color in acidic conditions, and a different color in basic or alkaline conditions. Phenolphthalein indicator is actually colorless in acid, but a deep red color in alkaline conditions. Indicators come in liquid form, like the one I used here. There are different types, including universal indicator, which is a mixture of a number of different indicators, so it can be used to measure pH. Some plant pigments, like those in red cabbage, can act as indicators. Indicators also come in the form of strips of paper, like litmus paper, which you've probably used before in the lab. Some litmus paper just tells us whether something is acidic, basic, or neutral by its color change. Other types of paper indicator show degrees of color corresponding to different pH values, so they tell us how strong or weak an acid or base is, or whether what we're testing is neutral. Certain indicators change color at a very precise pH level. These are useful in analytical chemistry, when we're trying to determine exactly what concentration or what amount of an acid or base is in a substance. For example, consumer goods, like antacid tablets. Indicators are weak acids, which take on one color in an acidic environment and a different color in a basic or alkaline environment. Indicators come in liquid form. Some plant pigments can act as indicators. Indicators also come as strips of paper, some of which simply show whether an acid or base is present, and others which show graded color changes associated with different pH values. Remember what happens when hydrochloric acid is added to water? This is the equation. We know our reactants were hydrochloric acid and water, but what are the products here? Chloride ions and hydronium ions. The chloride ion is negatively charged and could bond with any free hydrogen ions that are going round. In other words, it could act as a base. That is, accept protons, or H+ ions. In this reaction, then, we call chloride the conjugate base of hydrochloric acid, the product that is formed when the H+ is given away by the acid. Likewise, hydronium ions, which have a positive charge, can act like acids, giving away their H plus ions. In this case, hydronium is the conjugate acid of water. Here's another way of looking at it. Conjugate bases have the same formula as the acid less a hydrogen atom, and a decrease in charge of 1. Conjugate acids have the same formula as the base plus a hydrogen atom, and the charge increases by 1. Easy. We've talked about strong and weak acids and bases, but what makes them strong? Or weak, for that matter? When we used the example of hydrochloric acid and water just before, we saw the products were chloride and hydronium ions. Remember how some acids and bases conduct electricity? That's because they form ions when they react. The more a reaction ionizes, the greater its conductivity. Strong acids and bases will ionize completely. That is, all of their reactants will react to form ions, and they have a high conductivity. See? A weak acid, however, like vinegar, doesn't ionize anywhere near as much as hydrochloric acid when it's added to water. So strong acids are those that very readily tend to give up their protons. Hydrochloric, nitric, and sulfuric acid are all examples of strong acids. Strong bases are those that very readily accept protons. The oxide ions in magnesium oxide and the hydroxide ions in sodium hydroxide are examples. And you know what that means, don't you? Weak acids are not so quick to give up their protons, and weak bases don't tend to accept protons as readily as strong ones. Weak acids and bases don't ionize as much in solution as strong ones, so their conductivity is low. So it follows that if hydrochloric acid is a strong acid, which readily gives up protons and ionizes completely in water to form chloride and hydronium ions, the conjugate base of HCl is not going to readily accept protons to convert back to hydrochloric acid. This makes a weak conjugate base. Weak acids, however, like our vinegar, have strong conjugate bases in a reaction. When acids react, H+ ions are donated. The product is called a conjugate base because it can accept an H+. The product formed when bases react is called a conjugate acid because it can donate an H+. The more ionization, the greater the conductivity and the stronger the acid or base. Strong acids readily donate H+ ions. Strong bases readily accept H+ ions. Strong acids have weak conjugate bases, and weak acids have strong conjugate bases. An interesting reaction is when acids combine with some metals. Let's look at an example. Here, we've added hydrochloric acid, or HCl, to magnesium, and a gas is given off, which is hydrogen. But what else forms? Let's look at the equation here. We've got HCl plus Mg, which produces a salt, magnesium chloride, or MgCl2, and hydrogen gas, or H2. By putting a 2 in front of the HCl, we balance the equation. But just a point here, ow! This isn't what's known as a Lowry-Bronsted equation, because an H+ isn't donated to another substance. The hydrogen from the hydrochloric acid forms H2 molecules that are given off as gas. Here's another type of common acid reaction: acids and oxides. The oxides of many metals are known as basic oxides because they contain the oxide ion, which is a base or proton acceptor. It's an oxygen atom with a double negative charge. Soluble oxides combine with water molecules to form hydroxide ions, like this. When an acid is added to an oxide, salt and water forms. Here's an example. We take copper oxide, add sulfuric acid, and our products are copper sulfate and water. This is what happens. This is a Lowry-Bronsted reaction because the oxide ion has accepted 2 protons, or 2 H+ ions, from the nitric acid and formed water. Now, acids and carbonates. Watch this. I'm adding hydrochloric acid to sodium carbonate. We know there's a gas being produced here because it's bubbling. But what else is going on? We've taken hydrochloric acid and added it to sodium carbonate. There are reactants. And our products? Sodium chloride, which is dissolved in solution with water, and the gas is carbon dioxide. By putting a 2 here and here, we balance the equation. But there's a little more than meets the eye. This is a Lowry-Bronsted reaction because the carbonate ion, or CO3, is a weak base. It accepts a proton from each of the HCl molecules and forms carbonic acid, like this. But carbonic acid isn't stable, and it breaks up to form the carbon dioxide and water, like this. And finally, when an acid reacts with a hydrogen carbonate compound, salt, water, and carbon dioxide are produced again. Like when we add hydrochloric acid to sodium hydrogen carbonate, this is what happens. The products are sodium chloride, water, and carbon dioxide. When acids and metals react, hydrogen gas releases and salt forms. These aren't Lowry-Bronsted reactions because there is no proton exchange. When acids and oxides react, salt and water forms. This is a Lowry-Bronsted reaction. When acids and carbonates react, salt, water, and carbon dioxide forms. These are Lowry-Bronsted reactions. The carbon dioxide and water comes from unstable carbonic acid. When acids and hydrogen carbonates react, salt, water, and carbon dioxide form. Acids and bases, they're all around us. They share certain properties and have different uses. There are many things we can do with acids and bases in the lab and around the home. Oh, yeah, the oven. I got a bit carried away, didn't I? There's a lot more we could cover about acids and bases, but for now, I think I'd better finish my chores. See ya.